In this video, we're going to go over how to solve limits using algebraic methods, using stuff like arithmetic and algebra instead of graphs or charts to find what a limit approaches. Now, jumping right in, there are four main methods that you're going to want to use to solve limits, and you can almost break them up into kind of an order of operations. Now, you're going to want to do each of these in order, and the first one on the list is trig identities. Now, whenever you see something in a limit like sine of x or cosine of x, you're going to know that you should probably use a trig identity. But if you don't see one of these, then you can go ahead and move on to step number 2, which is going to be using the conjugate. Now, the conjugate is typically used whenever you have a function with a square root in the numerator. However, if you don't see a function that looks like this or has any kind of square root, then you can move on and try the third step, which is factoring. And I can make separate videos on all three of these different algebraic methods. If you guys want, just let me know in the comments. As I won't be going over them as in depth in this video, but I will be showing an example for each of them just so you can have an idea of what to do. Now finally, if you can't do any of these three things, you're going to go ahead and just plug in whatever the parameter of the limit is. And in my last video, I did explain that the parameter of a limit is simply whatever that value is that it's approaching. So in this case, c. Now I'm going to go over each of these algebraic methods in turn, starting off with plugging in. So again, we're just going to be plugging in the parameter, which in this case is 1. And when we do that, we get 2 times 1 squared. Now, 1 squared is just 1, so we get 2 times 1, or 2. Now, we can actually prove that this is what the limit approaches if we go ahead and look at a graph. Here, we have a graph of y equals 2x squared, and if we go ahead and find x equals 1, which is right here, and then we go ahead, using the magnifying glass method, zoom in on the function at this point until we get infinitely close to its value, which again is not actually possible, but we're going to zoom in until we can get a pretty good estimate. You can see that this function approaches y equals 2. So simply plugging in a number did get us the right answer in this. Our next method is factoring. You're usually going to use this method when you have some kind of polynomial or something involving x squared. So that's going to be a good sign that you might want to factor. And in this case, if we factor the numerator, we're going to get x plus 2 times x plus 1. And it's important to know that whenever you're rewriting a limit, you must rewrite the limit notation, because on the AP Calculus AB exam or BC exam, you may get points taken off for not keeping these consistent, especially on free response questions. Now, I know I kind of breeze over it here, so I can obviously make another video on factoring if you guys want, but just let me know. Now that we've factored, we can go ahead and cancel out like terms, because any number over itself or any expression over itself, such as x plus 1 here, is just 1. Which leaves us with the limit as x approaches 2 of x plus 2. Now that there's nothing left to do, there's no square roots, we can't use the conjugate, there's no trig functions, we can't use trig identities, we have nothing left to do but plug in. So, we're going to plug in 2, we'll get 2 plus 2, which equals 4. Now the next method to solve a limit is going to be using the conjugate. And we can see here that we have a function with a square root in the numerator, but specifically a square root function that's being subtracted by something outside of it. So whenever you see this, that's going to be a telltale sign that you want to use the conjugate, and you're going to kind of get used to seeing this pattern as you do more and more of these problems. It just comes with practice. But essentially what the conjugate is multiplying the function by itself, except switching the sign of what's outside of the square root. So in this case, turning this negative 2 into a positive 2. And this is kind of just going to have to be something you memorize, although again, I can make another video on this if you guys want. But after this, there's nothing left to do except multiply these out. And it's going to be really annoying, but if you use FOIL method, it gets a little easier. So first we're going to multiply first by first. Square root of x plus 3 times square root of x plus 3 is square root of x plus 3 squared. Square root of x plus 3 times 2 is 2 square root of x plus 3. Negative 2 times square root of x plus 3 is negative 2 square root of x plus 3. And finally, negative 2 times 2 is negative 4. And the bottom is simply multiplying the same expression by itself, leaving us with x minus 1 squared. Now, we can go ahead and simplify this in a few ways. First of all, the square and the square root here cancel out, leaving us with just x plus 3. Then, here we have positive 2 root x plus 3 and negative 2 root x plus 3. And since these are the same thing, subtracting one by the other is just going to give us 0. Which means we can just put that negative 4 right there and carry the x minus 1 squared over. If we go ahead and continue simplifying this, we get x minus 1 on the top because 3 minus 4 is negative 1. And now we can cancel out the x minus 1's on the top and bottom, canceling out the 1 on the top, and canceling out one of the x minus 1's on the bottom. This is finally going to leave us with the limit as x approaches 2 of 1 over x minus 1. And because we can't use the conjugate, there are no trig functions to use trig identities, and there's no way to factor this, we're left with nothing but plugging in. And because 2 minus 1 is 1, that means that the answer to this is 1 over 1 or 1. Now, the final method to solve a limit is using trig identities, and this is one of the trickiest ones to master, although it is the easiest to identify. So obviously you can see here that we have sine of x and cosine x in this function. But basically whenever you're going about this, you just have to memorize the core trig identities and then be able to plug them in when needed. Again, I can make a separate video on trig identities alone, but for this one, I'm just going to go ahead and tell you that we're going to need to use the identity sine squared x plus cosine squared x equals 1. And immediately, you want to find some way to plug this function in to this limit. So I can see here that we have a sine squared x on the numerator. So I'm going to try and get sine squared x by itself so we can plug whatever it equals back into this limit. Now, if we subtract both sides by cosine squared x, we're going to go ahead and get sine squared x is equal to 1 minus cosine squared x. Go ahead and plug this in here. Again, remember to rewrite the limit. We're going to get 1 minus cosine squared x over 1 minus cosine squared x. And now we have the exact same thing in the numerator and denominator. Anything divided by itself is 1, meaning this limit is also 1. Now, after going over the main methods to solve limits, we're going to talk about some of the properties. And if that doesn't really mean anything to you, you can think of properties kind of just as shortcuts to solve limits. So the first property of limits we're going to talk about is the constant rule. Now, this is just going to kind of probably look like a bunch of technical stuff you don't really understand for now. But basically what this is saying is that if you have a function that's being multiplied by some constant a, you can pull that constant to the front and then just take the limit of the function. Now this is going to be a lot more clear if we use an example. In this case, we're going to revert back to the first question we did, limit as x approaches 1 of 2x squared. We can kind of compare this to this property and see that in this case, the constant is 2 and the function is x squared. So if we bring that 2 to the front, we get 2 times limit as x approaches 1 of x squared. And we can just go ahead and take the limit as x approaches 1 of x squared. Here, we're just going to use the plug-in method because there's nothing else we can do. And we're going to get 1 squared, which just equals 1. 2 times 1 is 2. And we know that 2 is the answer to this limit, as we proved it both algebraically and graphically earlier. So you can see that the constant property does hold true. Next up, we have the sum property. And this essentially states that if you have a limit of two functions being added together, in this case we're calling them f of x and g of x, you can break it into two separate limits, one which takes the limit of the first function and add it to a limit which takes the limit of the second function. It's important to note here that the parameter for each limit stays the same, as well as the sign between them. So you can see here you're adding two functions, and here you're just adding two limits. Now, for this example, we're going to do the limit as x approaches 2 of x squared plus 3x. And in this case, our two functions are x squared and 3x. So we can break this into two limits, again, keeping the parameter as 2 for both. And because there's a plus sign here, we're going to put a plus sign between the limits. So if we use the plug-in method, we will get 2 squared plus 6, which becomes 4 plus 6, which becomes 10. And you can tell that this property applies if you simply use the plug-in method on the original limit. Now, obviously for this one, it's really straightforward, so you would probably just use the plug-in method to begin with. But for more complicated limits, which involve, more trig functions, maybe even logarithmic functions, this is going to be a lot more useful to know. So here, if we just plug in, we get 2 squared plus 6, which again, 4 plus 6 equals 10. These are the same thing, proving this property as well. This also holds true for subtracting functions, so if there was a minus sign here instead of a plus sign, you could do the same thing. Next, we have the product property of limits, which is the same as the one we just discussed, except with multiplication. Here, we've got kind of a funky limit, and again, you could just plug in here, but to prove this kind of little shortcut, we're going to use the product property. You might not really know what to do with this because the exponential function is weird, and it's being multiplied by 4x, which is also weird. But if we just break this into two functions and identify what those two functions are at first, it becomes a lot easier. I'm going to say that our first function is 4x, and our second function is e to the x. Now, using the product property, again making sure to keep the parameter consistent across both limits, we get this. Now, if we go ahead and just plug in, we get 4 times e to the 1. You might be confused by this at first, but you can literally just plug in the 1 as the x. And anything to the 1 power is itself, so we just get 4e. Now, we can go ahead and prove that this is true by simply using the basic plug-in method. If we had just plugged in 1 here, we would get 4 times 1 times e to the 1 power. Again, this becomes 4 times e, or 4e. Now, the fourth property, or little shortcut you can use for limits, is going to be the quotient property, which states that if you have a limit of a function over another function, you can break it into two limits, one taking the top function, which you divide by a limit taking the bottom function. Now, here's an example to go with this problem. This limit is going to look pretty scary at first, as it involves a polynomial on the top, and then there's a binomial on the bottom. But we can go ahead and use the quotient property to make this a little easier. So if we break it into two limits, again keeping parameters the same, we get limit as x approaches 3 of x squared plus 3x plus 2 divided by the limit as x approaches 3 of 2x minus 4. Now we can go ahead and use the plug-in method, as there's no way to use any of the other methods here. This still kind of looks pretty weird, so we're going to break this down even further and take each of these limits individually so that we can plug them back in later. So first, we're going to use the plug-in method here and find that we get 3 squared plus 3 times 3 plus 2, which comes out to 9 plus 9 plus 2, or 20. So we know that this limit equals 20. If we go ahead and break down the other one, we get that we can also plug in the parameter here, which becomes 2 times 3 minus 4, or 6 minus 4, or 2. Now, noting that these limits each equal their respective values, we can go ahead and plug that in. Here, this is going to equal 20, and here, this is going to equal 2, giving us a final value of 10. Now, the final property of limits is the composite function property. This is probably the most complicated one and probably the trickiest one to get down, but after I explain it, it's definitely going to become a lot clearer. So basically, if you have the limit of a composite function, which is just when you have a function that has a function inside of it, you can pull out the outer function outside of the limit. Now, this doesn't really make sense just looking at this complicated property. You really have to use an example. So in this case, we're going to do limit as x approaches 1 of the natural log of 2x. Again, my introduction to calculus video covers natural logs and exponential functions, so if you're confused on those, you can go ahead and check up on that. So here, we can go ahead and name the outside function, f of x, as ln of x. And we can name the inside function, g of x, 2x. Because ln is on the outside, 2x is on the inside. If we use the composite function property, that tells us we can bring this ln out to the front, just like we did with that constant earlier. So now this is going to give us the natural log of the limit as x approaches 1 of 2x. You can also just think of this like the constant rule, except with the natural log. It's very similar bringing it out. So now we'll take the limit like usual, just leave this ln here, but we don't really need to do anything with it for now. We plug in 1 and we get 2, giving us the final value of the natural log of 2. So that'd be how you could use a little shortcut to solve this limit, which initially looks pretty hard, but is actually easy once you figure that out. Now, I hope you guys enjoyed this video about how to solve limits using algebra, going over the different methods and properties. Make sure to leave a like and subscribe if you enjoyed, and definitely comment anything that was confusing or which I can explain in another video. Thank you.